Welcome everyone. Today's lecture we are going to look at an example problem of bending in 2 dimensions. We will look at a rectangular beam that is subjected to a bending moment in an arbitrary direction, and we are going to look at two things. One is find out what is the maximum bending stress in this particular beam because of the moment that is being applied, and also figure out what point in the cross-section actually has the maximum tensile stress and the maximum bending stress. So that's all going to be our objectives for this lecture. So finding the maximum bending stress and finding the locations where the maximum tensile stress occurs and where the maximum compressive stress occurs at a particular cross-section. Okay? So here's the problem. It's again a very, very simple problem. All we have is actually kind of a cantilever type of beam, okay, that has a rectangular cross-section as it is shown here. So the height of the cross-section is 50 millimeters and the width or the breadth of the cross-section is 40 millimeters. And you are applying a force P of 500 newtons in the YZ plane. Okay, so if you look at the cross-section here, then this force is acting at an angle of 30 degrees with respect to the Z-axis. Okay, and the magnitude of that force is 500 newtons. Okay, and we are asked to find out the maximum stress in this cross-section AA, which is 150 millimeters from the tip of the beam. And the second thing we are asked to find out is the location of the maximum tensile stress and the maximum compressive stress due to this force of 500 newtons, which essentially causes moments in two directions, My and Mz. That's we will look at later. So the one thing that I want you to notice that whenever you have bending, you are going to have both compressive and tensile stress in the same cross-section. It is not like axial loading, where the stress is uniform. Okay, so when you have bending, you are going to have both tensile stress and compressive stress. Okay, and these are going to occur in different locations. So we are going to find out where the maximum tensile and compressive stress is going to occur. Okay, so what do we do in problems like this? There are two ways to approach these problems. One way is that you know what is the force, you know what is the distance of that force from the cross-section or the centroid of the cross-section that you're looking at. So you can find out what is the R vector, and then you can find out what is this force F vector. So you can do R cross F and find out what is the moment due to that force in that cross-section, and essentially find out what components of moments are present and then approach the problem. So you do R cross F to find the moment at that cross-section and then solve the problem using that. The other way, something that I sometimes prefer, is actually you decompose the force into the two directions. In this case, you have the force in the YZ plane. So you have a component of force along the Z direction and a component of this force along the Y direction. So you decompose the force into forces in the Z and Y direction, figure out actually what kinds of moments they are going to cause, find out those moments, and then solve the problem. Oh, that is the approach that we are going to take today. Okay, so if you have this force P of 500 newtons acting at the centroid of this cross-section at the tip of the cantilever, the force in the Y direction is going to be P sine 30, okay, which is going to be 250 newtons, and the force along the Z direction is going to be P cosine 30, which is going to be 433 newtons. So essentially you can think of now as two forces acting on the tip. One is 250 newtons along the Y direction, and the other is 433 newtons along the Z direction. Okay. Now, once you have that, you can then try to figure out what kind of moments are going to be caused by these two forces, Py and Pz. Okay. And if you go back to your statics, you will realize that this Py, the force along the Y direction, will essentially cause a moment along the Z direction, will cause an My. Similarly, the force Pz will cause a moment along the Y direction. Okay, so if the force is along a particular direction, it can't cause a moment along that direction because M is R cross F. It has to be perpendicular to the direction of the force. Okay, now once we know that Py is going to cause an Mz and Pz is going to cause an My, let's find out actually what this My and Mz are going to be at the cross-section that you're looking at. Okay? So what do you do? How do you go about doing that? So what you do is, we take a section, okay, at AA, and then isolate the free body to the right. Okay, so FB is the free body. Okay. Now, once you isolate the free body, what you know is that if you look at this force Py, it has to cause an internal shear Vy, which we will ignore because we are only looking at the bending stresses, not the shear stresses due to the direct shear that is applied on the cross section. Okay, so we don't have to worry about Vy, but Vy has to be equal to Py to preserve equilibrium. Okay. Now, what is going to be the internal moment? So if Py is acting this way, it essentially has a tendency to rotate the beam that way. Okay, let me just actually draw this again. So it is going to rotate the beam that way, which means that the resultant moment mz, or the internal moment mz, has to oppose that. So this is going to be the direction of mz. Okay, so that is why it is drawn in that direction. Okay, so mz is in that direction. Now, the question is, what is the magnitude of this mz, and whether this mz is a positive mz or a negative mz. Okay, that is what we are going to find out. Okay, so to find out what mz is fairly simple. You multiply Py by the distance, which is 150 millimeters, which is 0.15 meters. So that gives the magnitude of mz. So mz is going to be 37.5 Newton meters, and it is in the clockwise direction here. Okay, the question is whether this mz is a positive moment. Okay, it is a positive moment for the following reason. So if you look at this section here, the normal to that section is the minus x-axis. Okay, and now if you use your right hand rule and then curl your fingers along the direction of this mz, then your right thumb will be pointing into the plane of the paper. Okay, but your z-axis is pointing out of the plane of paper. Okay, so which means that it would actually be in the minus z direction. This moment mz is in the minus z direction. Okay, but the normal to the face is the minus x direction. So when you have the normal to the face to be minus x direction, a negative mz is considered positive. Okay, so that is why this mz is considered positive, even though it is pointing in the opposite direction to the positive z-axis. Okay, so that is something that is very important. So the convention and figuring out whether an internal moment is positive or negative is absolutely critical if you want to write the bending equation correctly and find out the stresses correctly and the locations where the stress is tensile and compressive. Okay, hopefully that is clear to everyone. Now let's look at the other bending moment, my. Okay, again, now we take a section again at AA. Okay, we take a section there and then isolate the free body, and this is how the free body looks like. Okay, and now if you look at the free body, there is a PZ acting in this direction, so there has to be a VZ in the opposite direction, right? And to counteract the rotation due to this PZ, there has to be a MY in that direction. Okay, so this direction here. So now if you use the same right hand rule, if you curl your fingers along MY, your thumb is pointing up, which is the direction of Y. So this MY is along the positive Y direction. Okay. But this particular face here has minus x to be its normal. So the direction of the normal is minus x. So even though you have a positive moment, it is considered negative. Okay. So a positive moment, or a moment along the positive y-axis with a cross-section whose normal is the positive x-axis, would be considered positive. But a moment, my, whose direction is along the y-axis, but whose face, the cross-section face, is along the minus x-axis, would be considered negative. Okay, that is something that is very important. So for the mz, it turns out that mz is in the minus z direction, but it's still considered positive because the face is minus x. Here my is in the positive y direction, but because the face is minus x, it is considered negative. Okay, so that is why this particular value, which is nothing but pz times 0.15, that is considered negative. So in this case, when you look at the cross-section here at AA, and then if you look at a cross-section that is pointing, so if you look at that as the cross-section and that is a positive x direction, you have a positive mz and a negative my. Okay, that is something that is very critical. Okay, so this is the cross-section that we are analyzing. So that is the beam, and that is the cross-section AA that we are analyzing. Okay, okay. So this is I would say one of the most important things that you have to do in solving a problem like this. Once you find my and mz with the correct sign and the correct magnitude, then the rest of it is fairly straightforward. Okay, so now if you look at this cross-section as I have drawn here, so that is your cross-section here. Okay, the normal to the cross-section is along the positive x-axis. Okay, and we know that based on our convention here that our mz is positive, okay, and my is negative. Okay, that is what we found in the previous part. Okay, so mz is positive and my is negative. Okay, so which means that the resultant moment here is going to be in this direction. Sorry, in this direction. Okay, because my is pointing downwards, mz is pointing to the left, which means that the resultant moment m is going to be in that direction. Okay, and what is the theta is going to be? That is fairly simple. Tan theta is nothing but my over mz. So my is minus 64.95, mz is 37.5. So you get tan theta to be minus 1.732, which means that theta is minus 60 degrees. Okay, so this is something that is important. This tells you what is the direction of the resultant moment at the cross-section AA due to the force P that we apply at the tip. Okay, so that is something that is very important. Okay. Now once you know my and mz, you know what theta is, the rest of the thing is fairly straightforward. Okay, so now to find out what is the direction of the neutral axis, we already know what the formula is. Y is nothing but Iz by Iy times tan theta times z. In this case, theta is minus 60. We have to find Iz and Iy. That is actually fairly straightforward. Iz is 1 over 12 times bh cube. Iy is 1 over 12 times hb cube. So there's a difference. Okay, so they're not the same. Okay, and that if you simplify, it's nothing but h square over b square. H in this case is 50 millimeters. B is 40 millimeters. So essentially 50 square by 40 square, that is 1.5625. Okay, so now your y, which is this equation, is minus 1.6525 times tan theta, which is minus 1.732 times z, so which is minus 2.706 z. So what it essentially means is that the moment is at 60 degrees, the resultant moment, but the neutral axis is at a steeper angle. Okay, and that is the neutral axis. Okay, so now we know that we already seen this, that for the rectangular cross section, the direction of the resultant moment and the neutral axis doesn't usually coincide. Okay, so this is a clear example of that. Okay, so now we know what the neutral axis is. So the neutral axis is the axis or the line along a cross section where the stress is zero. At every other point apart from this line along this cross section, the stress is non-zero. Okay, now the question is, how do you find out what is the maximum stress? And secondly, how do you find out which point has the maximum stress? Okay, and that is what we are going to do next. Okay, so if this is the neutral axis, okay, then you are going to have the point that has the highest stress to be at the farthest distance from the neutral axis. Okay, so here, just by looking at this particular diagram here, you can directly find out that it has to be this point and that point that are going to be farthest from the neutral axis. So if you draw a perpendicular from this point here and a perpendicular from that point there, that perpendicular distance is going to be the highest for any point in this cross section. Okay, so it has to be either the point H or a point F that essentially have the highest stress. Okay. Now the question is, which point is going to have a tensile stress and which point is going to have a compressive stress? Okay. For that, you need to think about how this entire thing is going to bend. When you apply a bending moment like this, okay, my right thumb is along the direction of the moment, my fingers are curling in. When it curls in, they essentially will push this point H. Okay? Push. Okay? Push means compressive. The opposite of that is going to be tensile. So if H is under compression, F has to be under tension. Okay? So H will have the maximum compressive stress and F will have the minimum or the maximum tensile stress. They'll be equal in magnitude but opposite in sign. Okay? So one thing that you can always know for sure is that when you have a rectangular cross section, the maximum stresses, maximum bending stress is always going to occur at one of the corners. Okay? Which corners will become obvious once you draw the neutral axis. So once you draw the neutral axis like this in this particular case, right? It's obvious that E is closer than H. G is closer than F. So it has to be H and F that have to have the maximum stress. And by using your right hand rule, you do your moment like this, see which point is getting pushed, that point is under compression. So we have figured out everything. Which 2 points have the maximum stress, and which one has the maximum compressive stress, and which one has the maximum tensile stress. Okay, so now we know which point is going to have the maximum tensile and compressive stress. How do you actually find out what the actual magnitudes of stress are? Okay, and that is actually fairly simple because we already know what is the formula for sigma x. So that is what we have been doing in the last two lectures, how to figure out sigma x as a function of y comma z based on the moments my and mz. Okay, so in this case, we already know what mz is. Okay, that is what we found out here. Mz is actually 37.5. We know my is minus 64.95. Okay, so we already know what mz and my are. We know what y and z are. How do you do that? We use the fact that the y coordinate of h is going to be the height of the beam divided by 2. So here it is 50 millimeters. Okay, so the y coordinate of h is going to be 25 millimeters. Okay, and the z coordinate of h is going to be 20 millimeters, half of 40. Okay, for the point F, the coordinates, the z coordinate is going to be minus 20 millimeters because z is going positive this way. F is on the other side. So it is going to be minus 20 millimeters. Similarly, the y coordinate of F is going to be minus 25 millimeters. Okay, so we know what the coordinates of both h and f are. That just comes just from the coordinate system. Okay, and once you know the coordinate of any point, you can plug in those numbers there and you can find the sigma x at that particular point. Okay, so once you know the coordinates of z, of h and f, you essentially plug those coordinates into this equation for sigma x because this sigma x equation is true for any point on the cross section. Okay, so you can put it at any particular cross section, at any particular point, and then you can get the sigma at that point. Okay, so that's what we do. So essentially we put the values for the point h, which is 25 millimeters of y and 20 millimeters of z. Okay, you put that there and you do the same thing for sigma x at f. Okay, and you find that you find your iz and iy, which is the moment of inertia. You plug all those values in, you find that sigma x at h is minus 7.12 MPa. Okay, and sigma x at f is positive 7.12 MPa. Okay, and that actually, in some sense, make sure that your initial assumption was correct. So if you think about which part you said is going to be positive, you said this part is going to be negative because your fingers are pushing there, right? So the stress at point H turns out to be negative, which is what you expect. The stress at point F, which you said will be positive, turns out to be positive. You plug those numbers into the equation, right? So your intuition and the equations match, which means that you are on the right track. Okay, So essentially every point in this neutral axis, if you think of this as this neutral axis here, every point on this side, that is going to be under compression. And every point on this side of the neutral axis, that is going to be under tension. Okay? And this point F is going to be under maximum tension. This point H is going to be under maximum compression. Okay? So everything works out. So your intuition is correct. The formulas bear it out. Now what you can also do is you can put the coordinates of point E here and point G here into this equation here. Okay? And check for yourself that the values of sigma x are lower in magnitude compared to these sigma at H and F. Okay? That also you can check and you will find out that is actually the case. Okay? So this essentially solves the problem that is interested in. So we know what the stress at or the maximum tensile and compressive stress are, we know where it occurs, and it matches with our intuition. Now, if this cross section was not rectangular, but rather say circular, okay, and we had the same moment or the same force applied at the end of the beam, the mz and my are not going to change because they don't depend on the cross section. They just depend on the geometry of the beam, or the length of the beam and how far it is, how far the force is from the point of analysis, right? So mz and my are the same. Now, what we found is that this is your z-axis in this case, that is your y-axis, okay, and your, let me use a different color here, and we know that that is your mr. Okay, and we know that that angle is 60 degrees. Okay, so if everything is the same, but instead of having a rectangular cross section, you have a circular cross section, these things are still going to be the same. Okay, but unlike a rectangular cross section, when you have a circular cross section, then the neutral axis and the resultant moment will coincide. So this will be the neutral axis. The neutral axis will not be separate, like this is the case here. Right? The neutral axis is separate from the moment. The neutral axis will be the same here. Okay? Now, in that case, once this is the neutral axis, you already know that everything here, every point here is going to be under compression. Every point here below this diameter here is going to be under tension. Okay? And how do you find out which point is going to have the maximum tension and maximum compression? It's actually very simple. You just draw a diameter through the point that is perpendicular to the neutral axis, and this point is going to be under the max compression, and this point is going to be under max tension. Okay? So it becomes very simple in the case of a circular cross section. Okay? So if I give you a problem where I give you a force or a moment acting on a beam, but instead of change it from a rectangular cross section to a circular cross section, your job becomes much easier. Okay, as long as you know that the neutral axis and the resultant moment are the same. Okay, or the direction of the resultant moment and the direction of the neutral axis are the same. Okay, hopefully that was fairly straightforward, and I will see you in the next class.